Here's an optimization problem. Suppose we have a box with the open top, so that's important, to be constructed from square pieces of cardboard 3 feet width by cutting out a square from each of the 4 corners and bending up the sides. Find the largest volume possible to have such box. So for this problem, you always want to draw a picture. So here's a picture. It's given to us, but this is what you should be imagining as you're reading through the problem. So this is, we're constructing this box, open top, so you don't need to consider the top. So you'll have 4 sides, 1, 2, 3, 4, and the bottom. So let's call that bottom. So 5 sides, 4 sides on the bottom, that makes it 5. Now, if you open it up, then it looks like this. And you're cutting off the edges. And then you fold it up. So you fold up this corner, this corner, this corner, and that corner. And it creates that box with open top. Now let's introduce some variable. Let's call this x, and this is x. Since we're cutting off a square, we can label x to represent the little edge we're cutting out, which means this is also an x. This is also an x because it's parallel to the other edge. And same thing, we have another tiny square on the bottom. Call this x, call this x. And the last one, to complete the full figure, we have x and x right here. So imagine that. And now let's think about the following. So we want to maximize the volume of this particular figure. So the volume of a square, or a box in this case, is length times width times height. So we know that the length and the width, so this is x, which is given to be 3 in this problem. So we can just call that to be 3. So this is 3, and then we're cutting off the edges, and the height is going to be some x, which we don't know. So if you just focus on the pieces on the left side, we need to find what is the length, what is the width, what is the height. Well, height we know, that's x, and we need to figure out what is the length and the width. So if you just focus on one of the side, let's say this one right here, let's call that length. So L, it's going to be, well, the entire piece is 3, but because you're removing this square and this squared, we can say that L happens to be 3 minus x plus x. Or you can say the length is 3 minus 2x. So that's one of the sides. So whatever 3 is, we're removing this and that. And the measurement of those we're labeling it as x. So I can call this 2x. Similarly, the width, let's call this side right here, this is the width. And that is also 3, as you can see it's labeled on top, which is the same thing. So the width will also be 3 minus 2x, because cutting off these 2 little square out, their dimension is x times x, so 2x. All right, so we got that. Now let's put that into our volume equation. So our volume equation now becomes length, so that's 3 minus 2x, the width, which happens to be again 3 minus 2x, times the height, that's x. So that's the volume of this figure, and this is what we want to maximize. So maximize this equation, which is the volume. So if I expand this and take its derivative, I get the following. So let's expand 3x, 3 minus 2x, 3 minus 2x. That's going to give you 9 minus 4, 3, that's 6. So 12x plus 4x squared times x, and then distribute the x. Your volume function is going to be 9x minus 12x squared plus 4x cubed. And we want to maximize this. We're going to find its derivative and find its critical numbers. So the derivative of the volume respect to x, it's going to be 9 minus 12 times 4. 12 times 2, that's going to be 24x plus 4 times 3, that's 12x squared. And then we set this equal to 0 to find critical numbers. So when I set it to 0, I have 9 minus 24x plus 12x squared is equal to 0. And you can pull out a 3 from everything, or simply divide everything by 3 on both sides to simplify. So by doing that, we have 3 minus 8x plus 4x squared is equal to 0. Now let's just rearrange the term so it's easier for us to factor and visualize. 4x squared minus 8x plus 3 equal to 0. Let's factor this. Looks like it is factorable. So if I try to factor this and solve for x, I will have, so this is 2x minus 1. And looks like minus 3 will do the job. All right, so these are the right factors. So that means x is equal to 1/2 and x is equal to 3/2. But we want to know which one gives us the maximum volume, the largest volume. So we need to test the first derivative function for this. So here's our real line. And we plug them in the real line. Let's say 1/2 and 3/2. So we're going to test the first derivative function. So we pick an interval and then test them. So let's go ahead and test. Let's pick 0 for this interval. And then let's pick 1 for this interval. And then let's pick 4 for this interval. Something within the interval to see which one gives us the maximum volume. So when you plug in this into your first derivative function, so our derivative function is right here. Let's pull this down. So we know that v prime of 0, it's going to be something like this. So I'm just going to go ahead and plug in 0 into each of these x. So here you have 9 minus 24x is replaced with 0 and 12x squared, 0 squared. So you see that this will give you a positive number. So let's call this positive interval. And you do the same thing for 1. So v prime at 1, that's going to give us 9 minus 24 times 1 plus 12 times 1 squared. And this will give you a negative number. And then just keep going in this way. We test the last number, 4. We have 9 minus 24 times 4 plus 12 times 4 squared. And this will give you a positive number. So negative here, positive here. So what that means is, so here we're going up and then going down. And then here you're going down and then going up. So this is a maximum, a local maximum for that function, which means in this context, it's going to be a maximum volume. So therefore, our maximum volume will be when the measurement is 1/2 for x. So what's the maximum volume then? Well, we can now plug this into our volume function. So the maximum volume occurs at x equals 1/2, which means the volume at 1/2, it's going to be, well, we simply plug this into our volume function. So our volume function is right here. So let's just take this downstairs. You can take this one or the one on the bottom. It doesn't matter. They're all the same. It's just one is expanded and the others aren't. Plug in x equal 1/2 for each of these x's. So you'll have 3 minus 2 times 1/2 and then 2 times 1/2. And here you also have 1/2. And then when you put these in your calculator, you'll get about 2 for the volume. So the maximum volume you can obtain with this measurement will be 2.